Okay. If everyone would like to take a seat, we're gonna start off with the last portion of our lineup for today. Thank you. If everybody can now take a seat, please, we're gonna start for the last afternoon portion of the symposium. Thanks. All right, so people are slowly coming in. So in the spirit of continuing on the language vision model spirit following Ashwara's talk, we have the chance to have one of our students here today, Saba Ahmadi, who's a master's student at University of Montreal and who has recently been awarded the Giro Excellence Scholarship. So congratulations on this. And today she'll be sharing with us her latest research on the examination of the robustness of reference-free image captioning evaluation metrics. Thank you so much. The stage is yours.
So, hi everyone, I'm Saba. I'm a master's student working with Professor Ashwarya Agrawal. Today, I want to present you one of our recent projects, an examination of robustness of reference-free image captioning evaluation metrics. So let's start with what is image captioning task. So image captioning task is a task at intersection of a vision and language field. And the model should be able to generate a description for the given image. For instance, for this example, one acceptable caption will be a boy smiling while jumping on a skateboard. So let's begin with how common metrics such as blue, rouge, meteor, and cider evaluate the quality of captions. These metrics are usually reference-based, means that they compare the candidate caption to a bunch of reference captions written by human annotators. And they also compute the scores for evaluating the quality of caption by computing lexical overlap between candidate caption and the reference caption. So the goal for this metric is to be highly correlated with human judgment. So these metrics have some shortcomings. Besides that, collecting human annotation is expensive, lexical overlap is not sufficient or even necessary for having a high quality caption. So let's take a look at this example. One reference caption for this image is, the airplane passengers are walking with their bags in the airport. So one failure case is when the candidate caption has low overlap with the reference caption, but it's still correct, like this example. Travelers in line in the baggage claim area. Another failing example is when it has high overlap with the reference caption, but the caption is the candidate caption is incorrect. Like the students are walking with their bags. So to overcome these shortcomings, recent works like ClipScore and UMIC propose a reference-free metrics to just overcome these shortcomings. These metrics are more aligned with how humans actually judge a caption. We as a human don't need some references to evaluate caption quality. So both of these metrics use large pre-trained models, which are used for assessing alignment between text and image pairs. CLIP score is based on the CLIP model, which is pre-trained on a very large data set, and they just use it as it is and they don't fine-tune it. But UMIC is based on the Uniter model, which is pre-trained on a very smaller data set compared to CLIP, but they also fine-tune it using some hard negative examples. So the importance of these two metrics are that they are reported to have high correlation with human judgment. However, the benchmark used to evaluate these captions do not necessarily involve differentiating between caption, which has significant overlap, but conveys very different meaning, like the example which you can see on the slide. We want to determine if this metrics can distinguish between the caption when they have a high overlap, but they convey a very different meaning. To examine these metrics for such scenarios, we use two kind of data set. Like the first VQA data set, and we converted question and answer pairs to caption sentences, and caption generated in this way are very unique in the way which even when the answer is incorrect, the big portion of the caption, which is based on the question, is still valid given the image. And we use GPTJ for this conversion. Also, we generate caption in control setting using the format of there is an object, and for the object which are presented in the image. And we extract this object using a COCO detection dataset. So we were interested in examining how different is the score assigned by these metrics to correct and incorrect caption using VQA dataset. So for VQA dataset, we just got both wrong answers and correct answer using like a VQA model, and converted them to a bunch of captions. And we saw that distribution of these scores for both of the metrics and for both incorrect and correct caption has a high overlap. The brownish area shows the overlap here. And so we tried to look into what may have caused this overlap. So we were curious about if these metrics are sensitive to fine-grained errors or not. So by fine-grained errors, as I just said, we refer to errors between a pair of correct and incorrect captions that have high lexical overlap. To obtain such pairs, we first generate incorrect caption using answers of a VQA model. And for the same set of questions, we use the ground truth answer to generate a correct caption about the image. So let's take a look at this example. As you can see, the incorrect caption, which is the title of the book is Muffin, got higher score by both metrics than a correct description of it. In total, both metrics fail about 46% of the times to rank correct caption above incorrect caption when the answer is fine-grained. So yeah, that's it. And we were more curious to see if the metrics exhibit different sensitivity to different types of fine-grained errors. So we did an experiment using VQA, a V2 data set. We generated a caption using ground truth answer, and then we generated 3 incorrect captions for it. So let's take the ground truth caption, this ground truth caption as an example. The color of the grass is green. First, we substitute the ground truth answer with a plausible but incorrect answer. So this question was, by the way, color question. So such as substituting a color answer with another color. Such as caption are plausible but not sufficiently visually grounded. Like the color of the grass is white. And second, we substitute the ground truth answer with an object found in the image. Such captions are visually grounded but not plausible, like the color of the grass is giraffe. And finally, we create a caption using a random answer, like the color of the grass is grill. So both metrics assign lower score to a plausible answer comparing to implausible caption, which has mention of objects from the image. This shows both metrics exhibit lower sensitivity to caption implausibility error and higher sensitivity to visual grounding errors. So now that we saw these metrics show different sensitivity to plausibility of the caption and visual grounding, we do some other experiment to check sensitivity to visual aspect of the caption. So we wanted to answer this question: are these metrics sensitive to the number of objects mentioned in the caption? And we use COCO detection data set to extract image objects from the image and use a caption template to form some captions. For instance, for this image, for this particular image, we create this caption. There is a person using one object, and with two objects, there is a person and a sport ball, and with three objects, there is a person, sport ball, and a baseball bat. As you can see here, clip score increases when caption has more object mentions of the image, and UMIC does not change that much. So also we check sensitivity to size of objects mentioned in the caption. For each image from COCO detection dataset, we created two captions using one small object of the image and one big object of the image. For instance, for this picture, we created two captions, one with a small object, there is a knife, and one with big object, there is a pizza. So both metrics demonstrate sensitivity to size of image relevant objects mentioned in the caption. However, to our surprise, clip score increases when the size of the object increases, but UMIC decreases. So we studied three different linguistic aspects of the caption, like negation, a structure, and length of the caption. To understand if these metrics are able to understand negation, we filtered out yes/no questions and created a correct caption when the ground truth answer with the ground truth answer, and also we negated the ground truth answer and we generated an incorrect caption about it. We observed that UMIC ranked the negated caption above the correct caption incorrectly in 44% of the cases, while clip score fell in 41% of cases. So we concluded that both metrics exhibit a weak understanding of negation. To check sensitivity of these metrics to the length of the caption, we first filtered incorrect answer generated by one VQA model for VQA dataset, and we convert them into the caption. Then we create a shorter but correct answer by converting only the question to the caption. So we can take a look at this example, for instance, and we observe clip score ranked short but correct caption lower than incorrect caption but longer caption in 53% of the cases. And this happened for UMIC in 62% of the cases. In conclusion, UMIC exhibits significant sensitivity to caption length. And okay, to change sensitivity of this, to check sensitivity of these metrics to sentence structure, we created some correct caption using ground truth VQA answers, and then we also shuffled them, like the example here. Like the man is walking in the street, and the shuffled one in the street, the walking is man there, like just shuffled one. So clip score fails to assign a higher score to correct caption than the shuffle one in 34% of the cases, whereas this occurs only in 9% of the cases for UMIC. So this indicates that UMIC is more responsive to sentence structure than clip score. So in conclusion, both metrics fail to detect fine-grained errors and shows lower sensitivity to implausibility error and higher to grounding errors. In terms of visual aspect of the caption, clip score shows high sensitivity to number of image relevant objects, and both clip score and UMIC are sensitive to the size of image relevant objects. And in terms of linguistic aspect of the caption, both metrics shows weak understanding of negation. And also UMIC exhibits sensitivity to caption length. And also UMIC is more responsive to the sentence structure. And the main takeaway of this project that is we need to be cautious when deploying these metrics. And we hope our findings will guide future research on developing more robust metrics. So I think we're able to take some questions. Any question? Thank you.